Today we're going to be talking about Numerical Integration 1. First off, quick review. There are a few different types of integrals. There are more, but the two most common ones are indefinite integrals, integrals with no factors of integration, like integral of x dx. Those always result in a formula. And definite integrals, with factors of integration, say the integral of 0 to 1 x dx. And those are always going to result in a number. So, for instance, if we had... Now, what is that number? For instance, if we had the integral of a to b f of x dx, then that makes that number, if we draw out the function f of x, this is f of x, that makes the number of this integral, the answer, the area from point A to point B underneath this curve. So this integral is that, the area of that. Next on, we're moving on to sequences. So a sequence is an infinite number, or an infinite set of numbers within a pattern. So for instance, if we had, 1, 2, 3, 4, and 5, that would be a sequence. Specifically, an arithmetic sequence. Arithmetic sequences are sequences where you're adding or subtracting to keep the sequence going. For instance, another one could be 0, 5, 10, 15, 20, ... It keeps going because it's infinite. That would also be an arithmetic sequence. The other type of sequence is geometric, where you multiply or divide. For instance, 1, 2, 4, 8, etc. Now, another example, we could have 1/2, 1/4, 1/8, 1/16. Those are all geometric sequences too. Now, the last one I'm going to cover is harmonic sequences. Those are ones where you're not adding, you're not subtracting, you're not multiplying, and you're not dividing. Say, for instance, 1 over 1, 1/2, 1/3, 1/4, etc. That would be a harmonic sequence. Now, there's also the Fibonacci sequence. 1, 1, 2, 3, 5, and 8, where etc., where each next number is the sum of the two numbers before it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and the next number would be 13, because 5 plus 8 is 13. Now, every sequence can always be represented with a formula or function, I don't know. But yeah, so this first one, I'm going to go in order. This first one we could represent by an, where an is the number in a sequence with n corresponding to which spot. So for instance, a3 would be the third number in this sequence. Oh, I knocked my camera over. Would be the third number in this sequence, which is 3 in this case. So an equals n, a1 is 1, a2 is 2, a3 is 3, a4 is 4, a5 is 5, etc. For our second sequence, it gets a little bit more complicated, but it's still not that hard. So we could find an by using the formula 0 plus 5 times n minus 1 in parentheses. So if we were trying to find the first one, which is 0, that would be 0 plus 5 times 0, because 1 minus 1 is 0, which is all 0. The second one would be 2. It'd be 0 plus 5 times 1, which is 5, and so on. Next up, we have our third sequence. This one can be represented by 1 times 2 n minus 1, to the n minus 1 power. Technically, you don't have to write the 1 times, but if you want to be extremely, extremely precise about it, then go ahead. If we plug this in, a1 would be 1 times 2 to the 0 power. Anything to the 0 power is 1, which makes it 1. For 2, it'd be 2, which means 1 times 2, which is 2. 4 would be 2 squared times 1, which is 4, and so on. Next up, we have our geometric sequence. The formula for this one, I'm pretty sure there's an easier one to write this, but this works too. AN equals AN minus 1 times 2. So if, for instance, we're trying to find A2, which is 1/4, we'd have AN minus 1, which is A1, which is 1/2, times 2, which makes it 1/4. Next one, we have this harmonic sequence. This one seems really tricky to figure out until you realize it's just AN equals 1 over N. A1, A2, A3, A4, so on. Now for our last sequence, the Fibonacci sequence, since it's the sum of the two numbers behind it, we just write it out that way. We have AN equals AN minus 1 plus AN minus 2. So again, if we were trying to find, say, A4, we'd have to do A3 plus A2. 2 plus 3 is 5, which is correct. Now for the last topic before we wrap this up, we're going to talk about partial sums. Partial sums are the sums of the number in the sequence, represented by an S. So for instance, in our first sequence, the 1, 2, 3, 4, 5, S3 would be the sum of the first three numbers, which is 1 plus 2 plus 3 equals 6. For our second sequence, we can do S3 again. It'd be 0 plus 5 plus 10, which is 15. For our geometric sequence, our first geometric sequence, we can do, let's do S4. That'll be 1 plus 2 plus 4 plus 8 added together, which is 15. We're going to skip the other geometric sequence for now, and we're just going to do the harmonic one. Say S5 would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, which, I don't know this one. I don't really want to do the math, so. So basically, for our harmonic sequence, basically, Sn would be 1 over 1 plus 1 over 2 plus 1 over 3, so on, till 1 over n. And that would be the end of our sequence. And that would be the same with all of our other sequences. But is there an easier way to figure out Sn for every sequence? Indeed there is. And this works for any sequence, I believe. Or maybe it's just arithmetic. I bet it's actually just arithmetic. Yeah. So, we're going back to our first sequence, 1, 2, 3, 4. So, Sn would be 1 plus 2 plus 3 plus 4, ... plus n being our last number. Now, here's what we could do. Though it wouldn't be, written correctly, we could reverse it and still get the same answer. So what we could do, technically, is Sn equals n plus n minus 1 plus n minus 2, ... all the way till you get back to 1. Now, if we were to combine these, look at this. We get m plus 1, m plus 1, m plus 1, and then this would be m plus 1, but it's not there. Everything adds up to n plus 1, so it'd be 2 Sn equals n plus 1 plus m plus 1 plus m plus 1, and you'd keep going. It'd go on as long as how many n's there were. Each one of these is a single n, so there are n plus 1s in this, so we could rewrite this as 2 Sn equals n times n plus 1, because if you have let's say 3 groups of 2 marbles, that's basically just multiplication. You don't have to go 2 plus 2 plus 2, you can just go 2 times 3, which is what we're doing here. If we divide both sides by 2, so we get back to our S of n, for every arithmetic sequence we have S of n equals n plus 1 over 2. Now to show the power of this, we could do, let's do for our first sequence, we'll do S of 9. We'll do S9. So S9 would be 9 times 10, 9 plus 1, over 2, which is 45. So S of 9 is 45. And if you want to add that up to make sure, you can go ahead and do that. Bye.